All right, so as the energy of this goes up, the energy of this has to go down. I think that's probably the best way to think about it. That if I insert the iron bar, that increases the energy held by the inductor, and it's going to decrease the energy held by the light bulb. Let's see. Yeah. All right, here I have two circuits. This is the current versus time graph for two circuits A and B. And I just want to know how their inductors are related to one another. These are LR circuits with a resistor, an inductor, and a battery, just like we've seen. And here I have circuit A in the blue, circuit B in the orange or red. And this shows how their energy gains, like how their current increases. And then later, after you take out the battery, how it decreases. Now remember, these are characterized by the time constant. And that time constant was it L over R? Tau is equal to L over R. It's a similar time constant like we had for RC circuits. This time just characterizes the rise of the circuit, the rise of the current in the circuit, and then also the decline, the decay curve. So is the inductance in circuit A bigger or smaller than the inductance in circuit B? We're sort of evenly split. Right now we are 4 of you have 1 and 4 of you have 2. Right, so you want to think about which one has the bigger time constant. Does circuit A have the bigger time constant, or does circuit B have the bigger time constant? If we think about this, circuit A reaches its maximum value pretty quickly, whereas circuit B reaches its maximum value in a longer amount of time. So how does that translate into the time constant? What does the time constant mean in this case? So which of these has the bigger time constant? And whichever one has the bigger time constant will also have the bigger inductance. That doesn't change your mind in any way? Okay, well, which one has the bigger? Which of these circuits requires more time to get up to its equilibrium resistance? B requires more time. See, it just A gets up there really quickly, right? But B requires a lot more time. So the time constant, the inductive time constant for circuit B is bigger than the inductive time constant for circuit A. So if tau B is bigger than tau A, write that down. So tau B is bigger than tau A, and I know that my time constant is directly proportional to my inductance. What does that tell me about the inductors in these circuits? Okay, good. I'm going to stop here. And don't choose A. Don't listen to him. All right, B is the right answer. I'm not going to tell you a joke, but I'm going to warn you about something. That tonight they're having a thing like over at the BCM where they're having like a beard auction. You know what this is? Have I told you about this? Huh? I don't know what's going to happen. So my wife said that she might come in at the last minute and just throw down a whole big wad of cash and say, no, we're going to shave it at all. But they get to choose how they want to shave it. So whoever wins the auction gets to choose how they want to shave it. So I think we throw it just like it really long. Right. But probably on Wednesday when you come in, it will be either completely gone or altered in some way. Almost certainly that's going to be the case. Okay? I just don't want y'all to be shocked. Because last year I did this. Huh? That's okay, you can be shocked. But last year I did this and my first graders, or they were kindergartners at the time. Like I came in and they were just blown away. They're like, who are you? But, so anyway, I just don't want that to happen to y'all. What's that? Right, yeah. All right. Okay, in this figure below, coil 1 is moved closer to coil 2, with the orientation of them are remaining fixed. Because of this movement, the mutual induction of the two coils. Remember, mutual induction, that just means like they're inducing a current in one another, they're inducing a magnetic field. If I move coil 1 closer to coil 2, as I'm moving it closer, how does that affect the induction of the two coils? Does the induction increase, decrease, or is it unaffected? Doing really well. If you're not certain, you can ask your neighbor. I'm going to go away at 55, 55. Okay, excellent. A is the right answer. For the simple reason that my magnetic flux is increasing. If I move this thing closer, I have more flux lines that are now passing through the same area, and that is magnetic flux, right? B is equal to B times A, or the interval of B times A. So my magnetic flux is increasing as I move those two closer. Okay, next one's on LC circuits, I think. Let me see. Yeah, we'll come back to this. We're going to get into LC circuits. I'm not really sure exactly how far we're going to get before the end of the semester. So today's the 20th. What's the last day of class? Like the class that made it. So how many class days do we have left?
Well,
This week?
5 after today, and then we have the 6th one is our test day.
Oh, okay.
Monday we come back.
And then we have another day just for review. So yeah, we'll probably get through this. We'll probably get into AC electricity as well. So I sent out some initial homework problems. Those will be good indicators of what you'll see on the test. Right? This is the first time I've ever taught this topic, so I'll stick pretty closely to the homework. And unfortunately, I don't have any other practice problems. But if you feel like you need other practice problems, I can scan some pages from textbook and just circle the ones that are similar. I might do that anyway. Some of y'all might do that. Might want some extra practice. Okay, I'll send there, and I'll just circle some ones, and I'll send you the answers as well. But I'm not going to make videos and all that jazz. Okay. All right. And we'll also have a day or a half a day where we have to take our general education assessment. Nothing to do to prepare for that. In fact, we'll see. We might just do that after the final. How do y'all feel about that? Because that way you're prepared for the final, you'll also be prepared for the assessment, and you'll do sort of the best that you could possibly do on it, I think. That might be best. It's 20 to 30 minutes, though, so that's the downside, is that you have 2 hours of final and then another 20 to 30 minutes. Whatever, right? Okay. All right. Y'all don't usually take the full 2 hours. Okay, okay, yeah, so we left off with energy stored in B fields. Now we're going to look at LC circuits, getting into oscillations, and this will carry us into AC electricity. So LC oscillations. So in an LC circuit, the charge, current, and our change in potential across our resistor will vary sinusoidally. And we'll see why that is later. It's a solution to a second order differential equation. But first, let's just sort of talk about how this is. If I think about my capacitor, I have energy in both a capacitor and an inductor. I think you had a homework problem where you had to sort of describe what happens in an LC circuit in terms of the energy, and so this is what that's getting to. In a capacitor and an inductor. And if you remember with a capacitor, that energy, I'm going to call it UC. This is like the potential energy that's stored in a capacitor. It was equal to 1/2 CV squared, or you could also say that it's equal to 1/2 Q squared over C. That's the energy in a capacitor. And similarly, in an inductor, I have this energy. which is equal to 1/2 Li squared. So that's my energy stored in an inductor. Oh, I'm sorry. Let's call this UE instead, not UC. UE because this is energy stored in the electric field. And I call this UV because what? It's energy stored in the what? In the magnetic field, right? So this is energy stored in the B field, in the magnetic field. All right, so if I think about this circuit where I have an inductor and a capacitor, and I'm going to start with the capacitor fully charged. I start out with something like this, where I have a capacitor that's fully charged. So I'll show that here with 4 positive, 4 negative. So I have a fully charged capacitor. And at this point, there would be no current within the capacitor, or excuse me, within the circuit. So I've just charged the capacitor with a battery, and then I take away the battery, and then I hook up the capacitor to this inductor. Now at this point, I'm going to have my maximum energy stored in the electric field, and then over here, I'm going to have no energy stored in the magnetic field. But then I start to bleed charge across the capacitor, or not across the capacitor, but through the circuit. All right, so I get a current that flows up here as I get charges that move from the capacitor over to the other side. All right, so at this point, I have less charge on the capacitor because some of that charge is coming through the circuit and then coming over here. So that capacitor wants to normalize so that it gets equal amounts of charges on each side, or rather, neutral charges on each side. So as a result, I now form this magnetic field. So I get a magnetic field over here. Oh, that's the wrong direction, sorry. Magnetic field over here. So now I have energy that's stored in the electric field, and at some point this is going to equal the energy stored in the magnetic field. All right, so I started out with maximum energy in the electric field, no energy in the magnetic field. Now I have equal electric and magnetic fields containing the energy. All right, so I go from here to here. Now I'm going to come to a point where I have no charges on the capacitor. I have maximum current. So all those charges have left the capacitor and I get maximum current. What is going to be my energy now in the capacitor? If I have no charges on it, what's my energy? In the capacitor? It's going to be 0. Remember, the capacitor energy is dependent upon the charge in it. So my capacitor energy is equal to 0. Excuse me, this is my energy in the electric field. And that means that my energy in the magnetic field is going to be equal to its max. And I also have maximum current. All right, so if I draw my magnetic field lines, I'm going to have a much stronger magnetic field here. So I just draw more magnetic field lines there. And then I go back the other direction. So I can go from there, probably know, sort of, get an idea for what happens here. This is an inductor, not a resistor. Sorry. Then I'm going to start switching my capacitor. So notice up here it had positive charges on top, negatives on bottom. Now I'm going to have negatives on the other side and positives on this side. Because when I get this maximum current and no charge here, this is going to start driving a current in the other direction. All right, that will cause me to build up charges on this capacitor. So now I will have a current in this direction. Is this right? Let me make sure I get my currents drawn right up here. Yeah, that's right. So now my current is in this direction. All right. Here I have a certain amount of current stored by the electric field, and a certain amount of energy stored by the electric field, and a certain amount of energy stored by the magnetic field. And I can say then that UE is equal to UB at some point in between. And it keeps going. So at some point you'll get a maximum current in this direction, and then that current will go away as the capacitor takes on its maximum energy, and it'll keep going through. Now we've seen a similar situation here before. I don't remember if we did this last semester. Did we do oscillating springs? I think we do that topic anymore. Did we? Yeah, we did sort of basic energy stuff, but I don't think we did actually the solution for them, right? The cosine omega t plus v, that kind of thing. I don't think we do that topic anymore. But we have a similar scenario with an oscillating spring, and so you can sort of think about it in terms of this. I'm going to redraw this sort of sequence of events through my LC circuit. Here I have maximum charge on the capacitor. If I have maximum charge on the capacitor, what is my energy stored by the inductor? It's 0. So I have UE is max, UB is equal to 0. We can think about this in terms of a spring. So if I have a spring that is fully extended, right, I can think about its, this is the equilibrium position, x equals 0, and out here it has v equals 0. So this spring has max PE and no kinetic energy. So in a similar way, we can think about the inductor. And you know what this spring does is it goes back and forth, and it trades back and forth between potential energy and kinetic energy, potential energy and kinetic energy. And so the LC circuit is going to do a similar thing. It's going to trade back and forth, not between potential and kinetic, but between what two types of energy? The energy stored by what? Right, so they're going to switch back and forth, And assuming that you don't have any resistance in the circuit, which isn't really a safe assumption, but assuming that you don't have any resistance, then that will go on forever. Because what will a resistor do to that transfer of energy? If I have a resistor in the circuit, as this current flows through the circuit back and forth, changing directions each time, it's going to lose, right? It has dissipative heating, right? Because if you run current through a resistor, P is equal to, right, P is equal to I squared R. It'll heat up that resistor and you'll slowly lose energy. We'll get into that in the next section when we have, when we get into LRC circuits, where we have a capacitor, an inductor, and a resistor. And then we'll get damped oscillations. But right here, if I look at either my energy or my current or my voltage, I'm going to have this oscillation that goes back and forth. Assuming that there's no resistance, it'll go on without losing any energy at all, forever or whatever. Let's look at the solution for this. Again, y'all get into this later when you do differential equations. By the way, when I was at my parents' house, my dad's house, we were going through some old boxes, and I found all my old college report cards. They weren't very good. Like in some of my years, I had B's and C's, and then I had a D that one time in engineering math. But later, I did a lot better. Like I sort of got my feet under me. But everybody makes bad grades sometimes, right? Well, maybe not everybody, but most people make bad grades sometimes. Yeah, like at one point, I had like a 2.8 GPA. I'm sorry, does that spoil your image of me? No? Okay.
No, that gives me a lot of hope.
Okay. Yeah. All right, so let's look at this circuit. I have this capacitor and an inductor. All right. I know that from the loop rule that the change in the voltage across the capacitor plus the change in voltage across the inductor, that these have to be equal to 0. This is just the loop rule. One of them has to be positive and one of them has to be negative so that they add up to equal to 0. I know that the because Q is equal to CV, right? And we had that for capacitors. Then this is equal to V is equal to Q over C. So I have Q over C plus, or excuse me, not plus, minus. What is my EMF of the inductor? I remember EMF of the inductor, L times something. Right, DI, DT. Right. Remember, your EMF of the inductor is greatest when the current is changing the most. So this is L di dt. This is equal to 0. Now, my I is equal to negative dq dt. Let me show you. This negative comes about because this is basically saying that the current I is equal to the change in the capacitor's charge Q. All right, so this Q that I'm listing right here is equal to the capacitor's charge Q. And so the current is equal to the negative of the rate at which the capacitor loses charge. Because that capacitor, the charge comes out of the capacitor, that is my current. So that's where that negative comes from. So I can write this then, continuing on, that Q over C is equal to, or plus L, if I is equal to dq dt, this is going to be d squared Q dt squared. And then that's equal to 0. All right, so I can rewrite this as d squared Q dt squared is equal to negative 1 over LC times Q. Okay, so that is a second order differential equation, ordinary differential equation, which you might get into in like the last part of calculus 2 or 3, but you'll get into it more in differential equations when you take it later. But I want to find a solution for Q such that if I take the derivative of it twice, I get that Q that's negative with some coefficient in front of it. What function do you think, if you take the derivative of it twice, will give you that same function, but the negative of that function? No. If I take the derivative of it once, I get it negative, and then I take the derivative of it again, and I get that same function that I started with, but positive. What function is that? Y'all know this. You take the derivative of these things like all the time in Calc 1.
Oh, the derivative of the trig function.
Right, your trig functions, right. So if I take the derivative, say, of a cosine function, I get negative sine, and then I take the derivative of it again, and I get negative, because that negative holds over, cosine. All right, so that's going to be the solution to this second order differential equation. And there are methods that you go through and actually determine what is the solution, but that's the basic idea, is that I'm looking for a function Q that will make this equation true. And it turns out that for this, my solution is going to be equal to Q cosine of omega t. Now, we haven't done oscillations before, so let me explain what omega is. Or first of all, when we go through, I'm not going to go through it here, but we'll get a function for I that's equal to I max times sine of omega t. And so that's going to be our function for our current in this LC circuit. Current in my LC circuit. It's going to oscillate as a sine function. Here, omega is a constant. It's going to equal to the square root of 1 over LC. The reason I have this is so that when I take the derivatives here, that I get this 1 over LC over the side. So that's why it's a square root, right? Because I get it twice. out of that cosine or sine function, and so I get square root of 1 over LC, square root of 1 over LC. All right. This omega is called the angular frequency. You have some homework problems where this comes up. But the angular frequency is related to your regular frequency, F. That regular frequency is just omega over 2 pi. Remember, this is the number of oscillations in a given time. It's in units of 1 over second. So it characterizes this function. What is a sine function? So sine of 0 is 0, right? So it starts right here. It characterizes how close those peaks are together. It's characterized by the period of this function. Don't worry too much about the angular frequency, but you might see it elsewhere. Actually, I think when you go in differential equations, you'll probably work a similar problem to this, where you look at physical scenarios. All right. Next time we're going to work through some problems that deal with this, and you'll see in your homework that you have some problems that deal with, for LC circuits, how that energy oscillates back and forth. And this will also be important when we get into AC electricity, looking at these oscillations, because of course AC electricity has an oscillating current and voltage. All right. Right now, we're going to do evals.